Okay, so welcome to the next lecture. We are wrapping up the discussion of the vector field a la Maxwell. So it's a massless vector field. And we've gone to quite a long song and dance to arrive at something. We took the Maxwell Lagrangian and added terms so that we at the end ended up with a bunch of scalar fields. So the vector field A mu of x satisfied the Klein-Gordon equation component-wise. And then we wrote down what we had. That's this wasn't supposed to happen. It won't happen now. Again, we wrote down what we know about the solutions to the Klein-Gordon equation and just did it for all the components. So this would be p to I cubed 1 over this beautiful normalization, and then we had a mu e vector e to the minus I p x plus a dagger mu e to the plus I p x. P0 is EP, and the EP for the massless field is just the absolute value of the momentum. And now, this is an operator, and these are operators. And since I didn't like them, I had to change them one more time, and that's why the ones I don't like get this extra decorator tilt. Why do we not like them? Because we want more than just the solution to the Klein-Gordon equation. We want to also have in some sense, a solution to the constraint. So we want the Lorentz condition to be satisfied somehow. At least classical. That's what we had. Klein-Gordon equation plus this. Otherwise, we wouldn't have the Klein-Gordon equation. So now we have to do this for the operator as well. In some sense, we had to realize that this didn't work with the commutation relation. So there's this thing here, a u e x a u dot and y. So this is the momentum to the a. So this should be delta, non-zero in fact. So what is it really? I delta minus I eta mu delta x minus y. So this is what it's supposed to be. In fact, in particular, non-zero. This constraint, however, together with the other commutation relation to the zero, demands that this bracket is zero, and that's a contradiction. So we couldn't impose this, and then we'll have to do something now. And the first thing was to redefine these A's and align them with the momentum in a way. So these are now 4 components in the direction x, y, z, and t, and we wanted something that knows where the p is. So one of the A's of this A mu vector was supposed to point in the direction of p, and then 2 orthogonal and 1 in the time direction. And then we had a basis that depended on the p, that was epsilon. So we have epsilon mu, and these are 4 vectors, and they are not labeled 1, 2, 3, 4. That will be simple. They are labeled S, L, 1, and 2. And S and L are names for directions. They are not variables where you can put stuff in. But this means the S direction, the L direction, like in X, Y, Z, the 1 and the 2 direction. And this stands for scalar time-like direction, and this stands for longitudinal. It's the direction of P, and these are the 2 transverse ones. So we have these 4 objects, and I wrote them down explicitly in a basis where the P vector goes in the Z direction, but then we argued, oh, you can do it, write down some equation that holds for any coordinate system, and in the homework you'll make this a little more precise. At the end of the day, we have these four objects, these four vectors, which satisfy, well, they're also normal in this sense, mu r times epsilon mu s beta mu, so normal contraction between these two vectors is plus or minus 1. We know that these plus or minus 1s with another eta, because it happens to be the same matrix as the metric. But those are in tables. The first entry is when the R and the S. The S is the big S, and the second is the L, and they're also complete, which I won't need here, but you'll prove this at home. So if you sum over R, S, L, 1 and 2, epsilon R, mu, epsilon R, mu, then you get beta mu. That's orthogonality and completeness. That's actually wrong. You have to take the sign into account. Beta RS mu. Now it's right. So it's these S comes to the plus again with the minus sign. Now it has to be a metric like this. And now having these objects, we can write down this expansion again with a mu in vector. Integral d dp 2 pi cubed 1 over square root 2 dp vector. And now here, or maybe even here, you convert for every p in your integral from the mu index to an r index, basically from a space-time index to a polarization index. And then you have here AR, no tilde, because these are the other ones, still depending on p, e to the minus ipx plus a dagger r p e to the ipx. Boom. And p0 is. Okay, so now this looks a bit like in the Dirac spinor case, where we had wave functions, the u's and the v's. Here it's the same epsilon for both terms, and the u's and v's, they had an s index. This is the r here. It labels the different spin directions, and then they also have a spinor index, which is the spinor index from the left-hand side. Here's a vector index of the vector. Anyway, these are like the wave function. We call them the polarization vectors. And these A's with index R create scalar photons, longitudinal photons, and transverse photons in the two directions. That's what they create. And you have never heard of scalar photons because they are unphysical. You only have these two, and we have to deal with it now. And the answer is in this constraint here. So where are we going? Hamiltonian. There was also something funny with the Hamiltonian. Let's write the Hamiltonian before we do this. H is an integral over. So originally it was the normal scalar field. Don't repeat too much. Yeah, I know. So it's this P vector, and then you can plug this all in and get A S dagger P A S E with a minus sign. plus AL B AL D and then 1 and 2. Could have written a sum, but maybe it's nice to see it once spelled out. So you have these things that look like number operators, but the scalar polarization has a minus sign. And you think, oh, this is not bounded below, but it is because the minus sign is part of the number operator. The whole thing counts the scalar photons. So that's not really an issue. And that minus sign is included because the AS has this wrong sign, a commutation relation, Q, it's minus, actually we write little s, like R here, and little s, so we have everything, and we have minus, no I, beta, RS, we have 2 pi, so 2 pi cube because it's momentum space, and then we have RS delta 3 T factor minus Q factor. Now, they again look like number operators because A with A dagger is kind of a 1. This has 3 minus 1s, but this is 3 times good and 1 times minus, and the minus is for the first entity for the scalar. So the scalar photon has the wrong sign here, in quotation marks the wrong sign, but this means that the whole thing is actually the number operator with this thing. So that has positive eigenvalues. However, this nasty minus sign makes the norm of a scalar photon negative. The norm of this state is negative. Let's just leave it at no. I was going to say let's just say this. But I think I have to be more clear. This is what I'm saying, right? The norm is negative. But what I want to see, how this comes about, if I do this norm thing, then this is the complex conjugate ASP, so here's a P, and then AS P 0, and now we evaluate this using the commutation relation, turn them around, and A kills this, and the commutator is what's left, and the commutator is minus 1, or minus these 2 pi's and stuff. Minus, it really is minus 2 pi cubed, and then it's also delta of 0, and this. So here we said we normalize the vacuum, this is equal to 1. This is infinity, but we already dealt with this because we can smear it, and then it's just a positive constant, and there's a minus sign. So they have negative norms. Despite this being not a problem for the eigenvalues of H, the negative norm makes the expectation value of this H negative. Why? Because if you have in this state AS of H, and then this thing, right? You want to compute the expectation value of H for a scalar photon. Even though this is a positive number in the EP, so this is equal to 0, and then we have the A, and we have this EP, which I pull out, and then this P comes from which momentum this is, and this was just shown as negative, so the expectation value is negative. So the norm is really a problem. We don't want the norm. And the whole thing that follows is to get rid of this norm, get rid of the negative norm states. And that's this thing now. Applying the derivative to the expression down here gets the P down, and then we have a contraction of the P with the epsilon and with the A. And then we've shown that this condition really says, what does it say? Well, blah, blah, blah. At the end of the day, it says AS of P minus AL. This is a capital. So this is a small s, and usually this is the big S. But since, scale invariant, then I have little tails and heads. So that's a capital S. That's a capital S. This is the scalar photon, this longitudinal photon. And this combination, this should be 0. By virtue of this thing. But we can't just set them to 0. So what Gupta and Bleuler decided is, hey, we can just say, we don't set them to 0, but we say on all the physical states out of our Hilbert space, we want those, we call those physicals, which are annihilated by this combination. So the Fock space is created by all of the A's, all of them, with all 4 polarizations, but then we select those that are annihilated by this thing. Now one has to show that this is enough to get rid of the negative norm states. How are we going to do this? We will give this combination a name, A, and I call it G. And G stands for gauge. And it of course has a friend, the AG dagger, which creates things. But since and then we have another one, another linear combination, AU of P. This is defined as AS plus AL. So now, instead of talking about the scale in the longitudinal direction, we can talk about the direction G and U. U stands for unphysical, but you don't know yet that it's unphysical, and that's what I want to show now. I want to show that this condition, that AG has to annihilate all the physical states, implies that the physical state cannot have any AU excitations. Funnily, it can have AG excitations. Is that cute? Usually you would say, hey, if you have A is supposed to kill your state, then better not psi have any A's in there, because this isn't going to kill it if there's some excitation, if you want 0, so it shouldn't have. So if this is a G, you would have thought you can't have any G excitations. But that's wrong. We can't have the other one because of all these signs. And what we need to figure out is what is AG with AG and AG with AU and U with G and U with U. All right. So this thing with G dagger. Let's see. Now this is fun. G with G means AS minus AL, and then AS dagger Q minus AL dagger Q. I promise. Yes. All right. That makes sense. I just inserted it. And now, expanding this out, we'll have 4 terms. The first with the first, second with the second, and then the mixed one. First, second, then the mixed ones don't give you anything because of this delta. You have to have the same polarizations. S with S and L with L give you something. So this is, can I be sketchy? There's a question. Yell at me if you
Yeah, question. I don't understand how you got from the derivative of A to this up there.
From there to there?
Yeah, from
like this condition. Yeah. Well, this is I didn't do it again in detail. That's why you didn't see it. If I differentiate, I'll get the P from the derivative. Yeah. All right. So I get the P from the derivative. With respect to X, I get an I, it doesn't matter. And then I have P mu epsilon mu R A R of P. And the whole thing, I don't set the operator to 0, said that didn't work. So I really only want this between physical states, one left and one right. And I want the vacuum to be a physical state, so then I could put the vacuum here. This kills the a dagger term. Then I have only this. So in the end, I have these things because all the Fourier modes are independent. All right. So on this, and now I have to use the properties of my epsilon. So the epsilon is p dependent, and then this is the condition for all the p's, but this epsilon aligns itself with this p here, so you always get the combination I wrote there, scalar minus longitudinal. In this sum, this survives only the combination scalar minus longitudinal. Yeah, so you have to first look it up from the last problem where I do a quicker argument in one coordinate system, and then I say that the scalar product is Lorentz invariant, or you do the homework exercise, which is beautifully explicit, where you construct these epsilons in general, and no funky business with this Lorentz invariance. You just construct them, and then you'll end up with this equation. So let's say we have. So I was asking, can I be sketchy? So this is now an S with an S, right? This is a dagger. And then I have plus by minus, I have plus longitudinal with a longitudinal dagger. So this notation makes no sense, right? It should be right. This is the sketchy part. All I want to say that this comes with a minus sign and this comes with a plus sign. What's the answer? 0. Right? The commutation relation of S with S is whatever it is with the minus sign from here, and the other one is with the plus sign, so it cancels. That's why it could be sketchy. So A G with a dagger G commutes. So if you build your physical state, your state out of as many G's as you want, right? Here's the vacuum. I'll add more stuff here. Acting on this whole thing with an AG for testing. This is not the generic P. Oh, here. That's a state, vacuum, and then I act with these excitation or creation operators of type G, polarization G, which is this combination. Act. And then I will test, is this a physical state? I act with an AG because the physical state test is act with AG on it. And does it annihilate it or not? If it does, it's a physical state. So does it? Well, it goes right through them, as we just shown. So it goes right through here, and then it kills the vacuum because it's an annihilation operator. That's how we built our Fox space. Yes, it is. And if I had an A1, that's this polarization. I don't know what my P now is. P 1, 2, is it 3? Good question, right? Well, it's 3. and then A1, B4. I mean, as many as you want, and you can also throw in some two polarizations. So you can create them, the transverse polarizations and the G polarizations are physical, because this commutes. The other one isn't. Because AG of P with a U dagger of U doesn't. So the U has a plus sign here, so has a plus sign there, and therefore has a minus sign there. And therefore, I guess it won't be zero. It'll be something. It'll be non-zero. Yes?
Short question, the thing above, because if I act with the AG on this whole state where I have A1 dagger inside of it and A2 dagger inside of it, they don't commute, right? AG doesn't commute.
AG commutes with A1 and A2.
Oh, okay.
So the safe ground is all the R's is a different commute. S with L, S with 1, and because of this eta RS. So the scalar, the longitudinal 1 and 2 commute. The
Okay.
S, the G is a combination out of two of them. So that's a little bit tricky. And we see that G with U, suddenly it's different flavors. It's a U direction and a G direction, and they do not commute. I can write it down. So it is minus 2 because of sum of 2 pi cubed delta 3 p minus q. Now the sign, right? Yeah. So it's not, well, it's equal to this and it's not equal to 0. But now, then this means if I had an AU in here, I will erase it, I'll have to erase it, it will not go through. In fact, it will leave behind stuff and it won't be 0, and so we have to discard the state. And now we have our big Fock space reduced from basically stuff that's can be created by 4 polarization by 3. So now the good ones are AG, A1, and A2. And that makes, well, okay, that's one part of the story. I think we'll talk about the norm. I was going to say that the negative norm states have gone, but before that, we can already talk about this expectation value, which is kind of neat, I think. This condition up there, S minus L, if I put this to the other side, to the other side, I have AS is equal to AL this, right? So acting with this annihilation, it should be the same as with this thing. Now you can dagger this equation. So then you have this from the left-hand side onto a dagger S with any P, and this is this on AL dagger for any physical states again. Now you multiply these two equations like this, and this together, so this of AS with AS on this be the same on different states, that can be the same. I can use this equation on the first half and this on the second half, so it's the same as this AL. It could be complicated physical states, but this holds true for sure. And if that's the same, if this is equal to this, then the difference between this term and this term is 0. Now come to this side with a minus sign. And then we have 0 is this difference. So if you sandwich H with physical states from left and right, then we'll have here the first line exactly this condition. So this is equal to 0, so it disappears. The scalar photon and the longitudinal photon cancel. So in the contribution to the energy, if a physical state, these two things cancel, and the only thing that's left is 1 and 2. So here with our Fock space, where is it? There. So this is a physical state, and therefore my argument works. And if this is now used to compute the expectation of H, so here this long thing goes here and there, the first line will cancel. The G produces S and L excitations, but they don't contribute to the energy, and then they're worthless, really. I mean, not bad. That's not fair. They don't give you any energy contribution. That's what I'm. So, but they're there. Not really, they're worthless. They don't see that. And now the norm. How do we compute the norm? We did this, right? We computing the norm of such a long state is complicated because you have so many things to commute past each other, and then you let's just do one excitation, one of the G type. So if you have the norm, I want the norm of a G type excitation squared, so that is 0 AG P and then a G P. This is just as sketchy as above because you have P and P. Then these norms aren't really they're not normalizable. I would have to put wave packets like we said last time, and then the formulas get a little bloated. But here we really only want the sign, and we can figure out whether it's plus infinity or minus infinity by doing this sketching thing. So now they commute. What does that mean? Here we got something with a minus sign, and we got a negative norm, and we weren't happy. And now we have a well, the G particle. Now they commute. Yes?
It's 0.
It's 0. Whoa! Craziness. Now we don't have negative norm, we have 0 norm. Langsam nähert sich der Eichhörnchen. First we had positive and negative, then we got rid of the negative norms. Well, we don't know this yet. Let's see. One with like one, if you have one. One. This is the correct sign. You change the order, you get the delta function that's positive because of this negative in the eta, and then this kills it, and you're left with a plus infinity. So this is positive, and the same with the 2, and nothing else is in there. The U isn't negative at all either. If I had the U, we haven't done it, but U with U commutes too, right? U, if I computed a U with a U, then this means plus plus, and that's the same here. There's also 0. So the U excitation would also be a 0. So here I can write this. So we have here we have the basis, scalar photon, longitudinal photon 1 and 2. Scalar photons have negative norm, longitudinal 1 and 2 positive norm. Then came the physicality condition, a la Gupta-Bleuler, and they threw out a combination, which is this. They threw out this combination. You can't use this anymore. But you can use this thing. Then we have changed our basis to the GU1 and 2. And suddenly these single excitations, GU1 and 2, they aren't negative anyway, right? I mean, so, but, it's not that we threw out the negative one, kind of. I don't know. Well, these are only the single excitations. G and U are both 0. See, if you were only worried about the negative norm states, you would be tempted to think, well, then I can go with GU1 and 2, everything's fine. But no, the problem comes if you have a state where there's a G and a U excitation. If you have this stuff, these states aren't any good. Because now, if you have the norm of this is going to be really negative. Because the G and U, they don't commute and they have a minus sign. So what the problem was is not that we have a U excitation or a G excitation or something, but that we can't have both. And we could have thrown out the other sign. There's nothing better about minus than the plus. In fact, personally, I always like the plus. But here it's the minus sign which survives. And well, it matches to all the other signs in the game. And yeah, so that's the thing. This was just to clarify what happened to the negative. The negative comes because of the combination. This condition threw out the U excitation, so we don't have this problem anymore. So let's not talk about it. And what we are left with, we have the 0, positive and the 0 norm states. And if we combine now many G's, G's with 1s, 1s with 2s, will always be non-negative. Okay, so that was the first thing. We have now found oscillators, these, which produce states with at least not negative norm, and always a non-zero energy too. But what are we going to do with these AGs? So the thing is, here it's suggested by this observation. If you take one of these states, no matter how many AGs you have in here, you won't ever see them in the expectation value with H, right? Because of the condition they get canceled here. So it's only this that matters. So what this makes us believe is that they don't really matter. If you add them to a state or not, it seems to be the same thing. So let's investigate that somewhere. So if we have a physical state, let's say this, we have a state, physical I, T. This is equal to a physical state made only of 1 and 2, well, only of transverse photons. That's this polarization photons. So it's 1 and 2. But they don't have any G's. It's 1 and 2. Physical says there's no U anyway, and so on. And now I'm going to add to this a state that is physical but contains the G's. So now I have phi T, and I add, however, a physical state that also contains G excitations. I'm happy with at least one. So that one I make explicit. I'm going to write it here, AG of your favorite momentum, just any, and then the rest I don't care, it's any physical state. Now, I want to show that this state, what do we call this thing now? phi t prime. So this is the state we had. We added stuff to it, and it's a new state. And now my claim is, if you take this thing in a scalar product with another physical state, this should drop out. This is, of course, by definition, physical state times the phi t plus the physical state, a g dagger of p. With that, so sorry, this is not the same. This is a physical state trying say, because now here comes another physical state, so there's a different one. There we go. Now, what do you say about the second term? Say something?
0.
Why?
The definition is AG without the dagger on a physical state 0, and
Yes,
the dagger acts to the left.
exactly. So you can use the dagger, the A acts to the left on a physical state. And there, so this part is 0, and therefore, in the scalar, this is super general, right? We had this was our like good. This is a data we liked. We added a very arbitrary thing. Only what we said was it has to be a physical state and it has to have at least one G excitation. And it didn't matter in the scalar product with anything else physical. And the same, of course, would work on the other side. So I can have, if I have two physical states without these. Okay, so what the notation? If in words, if I have a state that has only 1 and 2 photons and another one 1 and 2 photons from the left. Here, this is only transverse and transverse. Aha, let's write trans, right? So transverse. That's kind of what we like. I could have added to the right, as we just said, but also to the left. You can just extend this thing, this one, plus anything that has G excitation. I don't know, maybe it's more clear in the homework. This is AG, so yes, now we have here a state which has a transverse excitation added to it, G excitation added to it, and then on the other side as well, transverse prime plus AG, this. And it's the same. So you can always add these things. And it's the same for all scalar products. And even if you stick in an operator in between them, it often also doesn't matter. What does that mean? That doesn't sound promising often. I want always. But that's not true. It's not always. It is whenever you put something in between that is gauge invariant. So well, there's, you know, the physical ones, so the physical ones that make any sense. The Hamiltonian, for example, you put it there, these extra terms don't matter. If you wanted to know what is the expectation value of a physical state of a physical state, phi, then it does matter if these things have a G excitations or not. Because A is not gauge invariant. A changes under a gauge transformation by a derivative of some function. And this extra term will then pick up this. So for all gauge invariant observables, the expectation values also don't care about adding something like adding G excitations to it. And then people said, let's consider equivalence classes. Let's say a physical, like a state in our theory that we have to worry about, that corresponds to nature, is not any one of them, a single one, but a whole equivalence class of them. And the equivalence class is your state plus anything else with G excitation. Where do you like this? This word in there. So a physical state is equivalent to a physical state prime if and only if, let's get defined, the difference P phys minus P phys prime, the difference is one with a G excitation. If the difference is a G excitation thing, let me write it and delete it in a second, so don't copy. If this is a AG on something, bring this to the other side, so you have a physical state, and the other one, this is exactly this equation. And so you don't feel this extra part, and then you would say, okay, they are equivalent. But a different way of saying that the difference is something with a G excitation is to say, oh, the norm of this has to be the norm of this, but the norm of this is 0. So you write 0. Two states are considered physically equivalent if the difference is a 0 norm. So if you can add, if you have a physical state, you can add to it any of those null states. 0 norm states are also called null states. I can add it. So you might as well then, if you have this freedom, throw them out altogether. Never add it because it's your choice. This is picking a representative. These are now equivalence classes. So if you have one state that's physical, you can have another one that's equivalent to it by just adding a null state. And then build your whole class, family of states that are all equivalent. It's an equivalence class. And any state out of this class is as good as any other. That's what an equivalent means. And then picking one means you have a representative of the class. And if you want, you may pick always that representative which doesn't have any G excitations in it. And therefore, you can say the really physical states are just the ones with 1 and 2 excitations. So you can restrict yourself to this, the P's are, yes.
Why do we have many states with norm 0 anyways? Does it have to do that we have like our eta here somewhere that's just giving us, I don't know, like something, it's not a real norm, but like a pseudo norm.
Probably yes. So all the trouble from the start. So it was a week and a half discussion. So it's really hard to say where exactly this problem. But if you wanted to where the problem is, then it is an indefinite metric. So the eta mu is the problem, right? It's plus, and that made the time, the nasty time, which is the problem of everything. The non-unitarity of Lorentz transformation, it's just a sign, it's e to this, that is always the thing. But somehow it works. Relativity wants the sign, and if you want it to have a covariant, then you have to have them all at once. It's the sign. A little differently, like throwing out the U excitations is a consequence of this gauge invariance. And throwing out the G excitations, the zero norm states, is a consequence of the residual gauge invariance. Because the first thing here, where is it? This D mu, A mu equals zero. This was the Lorentz gauge, and that got rid of the A mu excitations. But then we have said, even if you have Lorentz gauge, that's not totally fixed. You could add, so if I have A and I go to an A prime, which is that A plus the derivative of the what's called alpha. So and if this is Lorentz gauge, and I want that this is Lorentz gauge, so the D mu of A and the D mu of A prime are both zero. It still leaves the function alpha, which satisfies the wave equation. That also here. So this is what I'm saying. If you have something in Lorentz gauge, I want to do this transformation, and this A is in Lorentz gauge, which means this is equal to zero. Now I do the transformation, I get a new divergence, and if I make sure that my gauge parameter satisfies the wave equation, and it's zero, so it leaves the new one also. So there's a residual, and if you fix that residual thing, you'll get rid of the AG excitation.
Sure. It's just like that our norm in this case is like not a normal norm anymore, right? Like the norm for a Hilbert space.
Yes.
I don't know what it's called, but like, yeah, it's just like that's where it was like, oh, okay, I have to consider that.
Right. Who was first?
Yeah, so maybe one follow-up question. So we have to, like, if we build the quotient here and consider these equivalence classes, so this norm becomes a real norm. So we only have the zero state to have norm zero, right?
Yes.
Okay. I think that's also kind of this question, because previously we couldn't really call this a norm because we have different states that have norm zero, right?
Right, and now there's one equivalence class, which is the vacuum.
This is the
Which
true
has-
state.
So in this thing, we could have one that doesn't have any transverse excitations. So it is the vacuum, and then this equivalence class is this, together with all the AGs acting on it, and this class has norm zero, and that's okay because the zero vector has norm zero, and all the others have positive, but all the others have to have here at least one of them, and that's positive.
I'm a little bit confused on like how far we can choose a representative of this equivalence class, because you said earlier that when we calculate the expectation value of a random operator, then the AG are relevant, or they will be picked up from this operator.
Yes.
So I'm a little bit confused, like on how far we can choose this representative.
Yeah. Exactly. When you want to compute expectation values of gauge invariant
Ah, okay, just in
operators,
that case.
then you can pick whichever out of your class. If not, then you kind of parameterize them,
Mhm.
which is awful, but you wouldn't come. Yeah.
Thank you.
So yeah, that's the story. It is lengthy. The upshot is, however, very simple. It really means when we do scattering later with photons, we just choose what kind of photon we want. We just only pick the transfers. These are our representatives of physical states with transfers, polarization, and momentum, and then let's just boom scatter them. The A still has this long, so this big A mu. still has this very long expression with all the terms in it. So the A is still the A with all polarizations, like here. But for in and out particles that we prepare, we stick to these. You don't know what I'm talking about, but if you do quantum, if you do some computation of scattering things and there's an interaction, something's happening, then we'll have to use this operator again. And that will have a sum over all four polarizations. So as like virtual photons, those that are not things that you can prepare, they only appear in computations basically. They have all four polarizations. And then always, when it matters, the scalar and the longitudinal will cancel, and then, yeah. Now this is a good time to erase everything from memory. Right, now we have, I think, 7.5 lectures left, right? Have you counted? This is probably more or less full. And we are entering the hot phase interacting quantum field theory, right? This is going to be the hard, you know, you wondered why was quantum field theory hard? We haven't noticed this yet. Now comes the point. This is going to be conceptually and technically hard. A nightmare, right? So we have let's recap. Actually, you've just seen it. Let's recap what we've done. We have the scalar, the Klein-Gordon. Gordon scalar. That was this Lagrangian 1/2 mu phi with a mass minus 1/2 m squared phi squared, and it gave us these operators that produce particles. What did they produce? Neutral, spin, zero particles. Neutral in the sense of the inertial charge corresponding to phase rotations. This is real, so there's no phase rotation. You can't just multiply this by a phase because then this won't be there. If you want it, you have to have complex conjugation, then you have a charge scalar field, but let's leave it at this. Then we looked at the Dirac spinner. The L looked like psi bar I d slash minus m psi. And this had 4 components. And the it gave us these particles, A and B, S. So we have an A and a B type. That is the different electric charges, positive and negative. Your call, which is 1, which is positive and negative. So it's particle and a particle. And this S takes 2 values. This is the spin. you decide which direction, up and down or left and right. So we have charged, spin, 1/2 particle, and anti-particle. So that's what we have from the Dirac theory, and then we have the Maxwell vector field that we just discussed, and this is L. It's minus a quarter F mu nu, F mu nu, and then plus all the story that we added, and I call it GH fixing. We picked a certain specific one. What we picked was a constant. In fact, the constant is set to 1, and then d mu a mu squared. But you don't have to do it, and that's why I'm not writing it. I'll leave it vague. You can do other terms also, like other gauges, Coulomb gauge. And that's not, we didn't go through the Coulomb gauge quantization, which is again such a long story with the same answer. And this gave us a dagger R P vector, well, of course, a neutral. What else? A neutral vector particle. I'm even embarrassed to say it. So anyway, it's a neutral spin 1 particle with transfers. Transfers. Polarization. Well, this is 1 or 2, and that's 1 or 2, 1 or 2. An example for this would be electron positron. Example for this would be the photon. And we want, in the end, in 2 weeks or so, we want to do scattering of electrons, and then the force will be mediated by photons, and then we'll use exactly these 2 theories, meaning here we create an electron and then scatter and something happens and stuff. Right. Now these A's came out essentially by changing variables from the fundamental fields into another basis, and the commutation relations gave us the commutation relation of the fundamental fields induced the commutation relation for these operators and identified them as creation annihilation operators. And it's all needed to write them, we solved the equation of motion, and they were time independent Fourier coefficients because the equation of motion were simple, right? Like the solution to the wave equation, it's just the sum of exponentials, and the coefficients of the exponentials are constant amplitudes, and these are the amplitudes. Now, if you go beyond this, it all will change. So what does it mean anyway to have interactions? We have to look at we have to add something to our equations of motion. Just add a term. And then everything will change, so the particles won't remain conserved. Right, I guess this is what I'm gonna say. We looked earlier at the time evolution of the states. If you have a state that is created by one of them, then this has a utterly simple time evolution. It just multiplies it by a phase. And so they're all independent, they all go through each other. Now we want something to happen. So we'll add terms to the equation of motion, and then hopefully things change. But they also shouldn't change too much, because if they change too much, then all our interpretation of these things is completely gone, right? If you change, so we will change it a little bit. And what we'll do, we'll add things to here, which are in a way, in a sense, small. And the two theories that we're going to look at, we will mainly, so that means in the lecture, focus on the first theory is called phi to the fourth, phi fourth, so to the power four. Why is it called like this? Let's see. The Lagrangian is the Klein-Gordon 1/2 d mu phi minus 1/2 m squared phi squared, and now comes minus lambda phi to the fourth. That's why the name. And this is a theory, it's just a scalar field, and that would be a self-interaction. So there's this particle now interacting with itself. There's no other particle involved. We will just have the same and adding this interaction. And the other one is QED. And QED looks like this. It is the function 1/2 f mu nu plus the gauge fixing plus the electron content. So ID minus m psi. And these are now, it's a theory with photons and electrons, and nothing's happening to them. So this is just go flying, everyone. And then we add minus E psi bar gamma mu psi a mu. That's beautiful too, right? It has the mu index, talks to the mu index of the gamma matrix. The gamma matrix has spinor indices, which talks to these, and so this has everything in it. But it's also like the minimal things. It's nothing x no square, nothing. It's just psi a, and there is a parameter that controls the strength basically. If you set E is a parameter. E and L are numbers, like the mass, and they're called coupling constants. They say how much does things couple, interact. The coupling constant QED is the electric charge. So if the electron is charged, then they attract, or rather repel, I guess, to electron. Let's see what the sign says. It also depends on whether E is positive or negative, but because it's with the notes. Now, in these two cases, the equations of motion look like this now. Of course, the Klein-Gordon, but if you have this extra term, then it basically does the same thing as this mass term in the Euler-Lagrange equation. So I can just copy it. It'll be this term minus on the other side. So it's minus lambda over, and then differentiate 4 will be 3 factorial phi cubed. So that's your new equation of motion. It was what I was trying to say before. Equal to 0 had a simple solution where if you put massive wave equation, you could solve it. But this is just hopeless, yes?
I have one question. You said that we wanted to add something small.
Yeah, you can tune lambda, just make it 0.00001.
Isn't the problem that like we don't, is phi small?
I don't know. If it's big,
For that.
if it's, yeah, no, you're right. If it's big, I make lambda even smaller. This is
Lambda, I thought lambda is a fixed constant.
yeah.
Wouldn't that make problems for, like in different parts of phi, wouldn't that make a problem?
Yeah, I guess. You're onto. I mean, there's of course a story. basically we'll have to see. It goes to work that it doesn't make any sense to think it's small. I'm going to be honest, I'll do some computation and then see what I get, but it'll turn out that this isn't, see, there are also different regimes. Like you can look at, you choose the state and the observer that you want to compute. And if I want to compute, the whole goal of this QFT thing is to compute scattering amplitudes, probabilities for scattering events. And physically, it makes sense if you prepare your particles far apart. There's this particle collider, and you know, the beam pipe, and there's a particle here and a particle there, and they move this, and then they're going to collide there. But here, they're so far apart, I don't know, they look independent to me, like free particles. So that shouldn't matter, right, somehow. I mean, the overlap of their wave, you know, there's only one wave function, but it should have a bump here and a bump there, and then so the point is that we'll look at situations where our particles are so far apart that they don't interact. That's the story. Now you'll object, for you, this is a self-interaction. You know, it's not just the interaction between two different things, it's also this particle by itself. This particle will produce, you know, particles coming, and then such a term, you don't know what I'm talking about. Again, despite the four means, you can actually produce two things, and then they fly. These are the virtual particles, they can do stuff. They get the energy out of nothing, uncertainty basically, and then they can also annihilate, and then you have your particle back. And that was so quick you don't see it. It just happens all the time, and maybe if it could also happen there again. And funny things you can do, I guess. Everything, boom. These are called Feynman diagrams, just higher one. And that will change the properties of even one particle. So here I said I want the particle between two, the interactions between two particles to be small, so that I have free here and free there. But then there's also the self-interaction just on one side, and that will do something, and hopefully it will only change the values of these numbers here. And that's the whole story about renormalization. So it could happen that these interactions are so strong that it produces infinities. It'll do this all the time. So basically the interactions are so strong that you get infinities. Because you allow this to happen all the time and as quickly as possible and as quickly as it wants. So it forces a diversion. And then you have to set these things to basically zero to some power, and then these two things cancel. So that's how we get out of it. But it's a very long and complicated story. Let's just maybe I shouldn't to avoid this discussion. I mean, it was bad, but you could just say let's look at these theories. Period. Don't even expect something good to come out. I don't even expect this to be close to 3 year at this. I'm just writing this down. I haven't forgotten you.
Yeah, but like I mean you sort of like disproved what I was trying to ask or trying to say while I was asking. I'm just thinking it doesn't look so bad right now for me. Like I always think like, okay, all we need is that phi is bounded, and then we can set our lambda as small as we want. And like I was more like arguably a little bit agreeing here where I'm like, okay, as long as phi is bounded, which I don't have a like super great interpretation, but it makes sense, then we can probably set our lambda small. Yeah,
yes, we all set our lambda asymptotically to zero in renormalization thing. In fact, But it's, there's still a long way, right? This is a classical equation for a field. You know, we're gonna go step by step, then we have quantum fields, then we have their equations, and then we have observables, and then we'll see what the observables say. In fact, yeah, the whole story of renormalization will just touch, and then there's QFT two, where you make this more precise. But the touching means that these are not the final mass or coupling. This is just the parameter in the theory, and the real mass and the real electric charge will be computable, will depend on this. So you can't say, you said, oh, isn't this a given number? If it was, then it isn't. It's just the bare coupling, and classically it's the charge, but quantum it does thing. Now the equation of motion for the other theory here is just what we have d mu f sine mu. I don't remember. Mu equals 0 we had before. And now, if I vary with respect to A, I get also this term. Minus E, on this side probably plus. Minus E psi bar gamma mu psi. Let's check the sign, this doesn't matter. Minus, yes. And then that's the equation for A, coming out of this. And then we have an equation for psi. Varying with respect to psi bar, that is just I d slash minus m psi. This thing equals minus what? Minus E gamma. You can call it A slash if you wanted to. Funny, A slash psi. If it's this is the equation of motion. No, I realize that. Again, mine don't matter, but I think I might okay this. Because this goes to the other side, right? At this point, I just want to say the solutions are going to look different. We want to compute scattering. Goal is to compute scattering amplitudes. So we have an in-state with some particles of some momenta. One particular depth, and we call this an in-state. And then we want to know what's the probability of getting particles at the other end, at the out time. And it's V1 prime, V2 prime, dot. So this is the probability amplitude of scattering. Particles with, this is too long, this sentence. We have scatter particles with these momenta in an initial state to these. And I wanted to show you some pictures, how I like to think of these states. Because this in and out is a little tricky and used to confuse me a lot. What is that? P. And then you think of, these are Heisenberg states. These are states that are time independent. They label the state, and you have your operators that change in time. So what's really going on? What does it mean if you have this scalar product of an in and an out state? How is this going from minus infinity to plus infinity in time if it doesn't even change? So here's my picture. So first I wanted to do this pretty, get something pretty from numerics. So like look at this equation and do something honest, but that failed because it's just not pretty when you do it. You can of course do it numerically, but it's not pretty because you have like plane waves, and plane waves have constant amplitude everywhere. You don't see anything. So what I'm doing now is just a picture. I'm painting. I'm coming up with formulas that I just found beautiful to look at. This is no computation, but it is still not completely stupid. It is it makes sense when you do wave packets and all. So this is my state, the classical wave function. Even in fact, so the numerics that I have hidden here does something like it. In the free case, you could have this thing as a solution to the classical equation of motion, and then you have, well, let me show. So if there's I've just turned up just a normal wave equation. What happens if you do the wave equation? You have two bumps and they go through each other and they have bumps coming out. Boy. But then I wanted to use the equation with this phi cube term, and it just produced something that wasn't really exciting. So I came up with what happens here after my skating myself. And it's going to be like, isn't that pretty, right? So that's how I think about it. You have two particles coming, colliding, and they go like boom, and then they have produced other things. And they spread out. This is a collision. So that's just a picture, just to be honest. But this is more or less the story. And now at initial times, so now I have a 3D picture of this. The time box it goes here, and so you can see your two particles coming in. At the initial time, you have a P1 and a P2, and this whole thing at all the times, you call that your Heisenberg state, P12 in. The H is for Heisenberg, and that's in. There's no time dependence. The state is the entire picture, and the label in tells you should look at asymptotically early times to see what you have. So there you have the two, and then they scatter. So what is initially a P1 and a P2 looks like this and can produce a mess. The out, so now, the out is the opposite. The out is this picture. Then you go to asymptotically late times, and if you have there a P1 and P2, or P1 prime and P2 prime, then this is your state. And if you can trace it back with your equation, and then you have this. And so that is the state. This is essentially how this looks like. So a P in has these well-defined P's on top at initial times, and then out has they sorted there. Right? So both is a P1 and P2, or P1 prime, P2 prime, because what primes, but when they have a label in, they look more like this, and if they're out, they have this. And now we can compute the overlap between these two things. And that tells you when these two scatter, how probable, like make this mess up there as a superposition out of these states, right? They'll have to get this wavy picture, you'll have to superimpose many of them. And then this scalar product asks how much of a certain one is in there. The normal quantum mechanics thing, right? You have a state, and it's a superposition of some eigenstates of some operator, and then you ask, oh, what's the probability of measuring spin? Well, a half. And here too, and the operator you have here is the basically the Hamiltonian at late times, and then its eigenstates are these particle states. Here you think it's free, and then everything that we talked about now holds. You know, these states are down here, you would, what's that? What's that? I wanted to, you know, you have to prepare this state as an in state, so this mess as an and then if you scatter this, then this comes out. This is the unlikely thing. That's like the broken cup that comes up and then you have the it's like but in time reversal works here. And just to illustrate or contrast it with the free theory, if you have the free theory, then you have this thing. So this just goes through. So the P1, P2 in state is this, but it is also the P1, P2 out state. So there 100% of what goes in comes out in the same thing. So that's why it was boring. Okay, that's a perfect time to stop. I wanted you to have a picture of what we are doing, and then tomorrow we'll actually do it and get technical. Like the question that now arises is how on earth do we write formulas for these states? Because these creation annihilation operators came out of solving the equation of motion, which we now cannot solve anymore. And that's the exciting story of tomorrow. So yes, you can come back. Thank you. Oh, there's a